All right, so let's just finish up. This will be a pretty short section, and I'll just talk about vapor permeability. And so in the first step of really looking at building systems in whole system design, we are looking at the thermal envelope. And so once we do that, we can't just pick a building assembly and then start designing the whole wall assembly around it. I have heard of a few horror stories where very large multi-million-dollar buildings were designed, and they were designed without really checking the wall profile of the assembly. They created some fabulous ideas that were going to be really good thermal envelopes, but they didn't do any testing on them for vapor permeability and vapor drive. And several of the buildings got built and had incredible moisture problems. Other ones got into the energy modeling phase after they'd spent hundreds of thousands of dollars in design and found out that the wall assembly wasn't going to work. So what we're going to talk about, the first thing is just evaluating the vapor profile of the wall. And so the first thing we talk about is the permeability of the materials and the permeability of the assembly. And building materials are categorized as 4 different ways: impermeable, semi-impermeable, semi-permeable, and permeable, and it's all in the amount of moisture vapor that they will allow to pass through. And they're rated in what they then call perms, and anything that's got 0.1 perm or less is considered vapor impermeable, but anything greater than that, moisture vapor will pass through to some level or another. So we've kind of discussed on several occasions about the importance of making sure that we can control that moisture vapor, and we have to be able to look at this in our assemblies. So in order to do it, the basic steps are looking at the permeability of each component, and I've got a couple little assemblies in here we'll look at, and then identifying the least vapor permeable component. So of all the materials in a wall assembly, and I'll jump over to here's a sample detail of a wall assembly, you've got a lot of different pieces and parts to make that up. You've got to determine which one of those parts is going to be your least permeable. Then you've got to determine which direction your vapor drive is happening. And we've talked a lot about vapor drive and the absolute laws of physics. Remember the building science laws. Which way is our moisture going to go? High to low, higher relative humidity, lower relative humidity. Our heat is also going to go which way? Higher to lower, hotter to colder. In that convective heat transfer, there's also going to be moisture. So our climate zone is pretty absolute. We know that most of the time the vapor drive is going to be from inside out. You get to the other extreme when you're looking at some of the hot, humid southern climates, you know the vapor drive is going to be primarily from the outside in. Most of the country isn't that absolute, and so evaluating building assemblies and thermal envelopes is not quite that easy. That's just a rule of thumb. So again, identifying and assessing the drying direction and the drying potential. So assuming that how much moisture is going to get into that wall, and if it gets in, how can it get out? So for example, in this vapor profile, we have on the interior, we've got latex paint, 17 wall boards, about a 40, cellulose insulation 75, and then we've got a layer of 1-inch extruded polystyrene, which has got a perm rating of 1, an airspace, which is relatively not rated, and then wood siding 35, and a 0.6 on the outside, which is oil-based paint. So within our wall assembly, not including the paint, our least permeable member is that extruded polystyrene. So if we think about which way the potential vapor drive can be, we can think about the challenges that we may or may not have. So for example, with this vapor profile in a moist, humid climate, where is the potential for condensation going to be? Between the siding and the XPS. Yep. So if we have a weather-resistant barrier, if we've got a rain screen or a water barrier behind there, and we get vapor drive there and bulk moisture, we're probably safe. What about in our climate zone? What are we going to look at for vapor drive? It's going to be inside the wall cavity. So that's where the potential problems are. Just another example. So here's one, and this is an example that I've seen in talking about unintended consequences. You've got that same wall assembly, and it's in say it's in a moist, humid climate, and then the homeowner comes along and puts a vinyl wallpaper all through the inside of several rooms of the house with a perm rating of 0.1. So it vapor impermeable. So in that same situation, you can see by changing that total perm rating of the assembly, we change basically where the condensation potential is and moisture buildup and damage in the wall. Does that make sense? So again, you can see if that vapor drive comes into the cavity, I don't know why I've got it accidentally in there twice. So what we're trying to do in a vapor profile, make sure we've got an assembly that avoids condensation, considering both the temperature and the moisture conditions. So looking at that, I just talked about the rules of thumb and said on that one, they're great when you get into the very extremes of our climate. So if we are in a very cold climate, we have a fairly consistent vapor drive. Some other rules of thumb that you may hear if you look at some, keep the outside of the wall 5 times as more permeable as the inside. That's great in some climate zones, but not others. The 10 times relationship, even in ASHRAE, in what we talked about the ASHRAE for energy performance, 90.1 and the 62 for IEQ. They actually have a standard for vapor drive, moisture migration, and controlled moisture. Even in the ASHRAE standard currently, in what they recommend, it ignores capillary moisture movement. So a lot of times you'll have that moisture movement that wicks up through the material. And then the biggest thing, and we'll get to this when we talk about the WUFI here in a minute, ASHRAE ignores the storage capacity of materials, and this is where building failures come, is in that storage capacity of the materials. When you build a building, and if you build a wall profile that may have this potential for moisture buildup, and whether it's just water damage or mold growth, it doesn't necessarily happen instantly. It's 3 years or 5 years down the road when it happens, and usually by that time, because it's inside the wall cavity, the failure is pretty catastrophic. So and I'm not going to spend too much time on this. So there's the rule of thumb, there's some of the standards, there's what's called the dew point method, and we'll go through this. We talked about this a little bit in our other class last semester. But calculating the dew point is actually fairly easy. You can know where the dew point is going to be by using if you know the temperature and the relative humidity, you know what the dew point is. And so if you can calculate what the relative humidity is, and by knowing the heat loss, and we talked about calculating conductive heat loss, you can extrapolate what the temperature is going to be inside your wall cavity, so you can determine potentially if the dew point is going to be reached inside the wall cavity. We do that with the psychometric chart, and you don't need to know how to use this. We're not going to start using this to talk about latent heat, but you just really need to know what it is. It looks, when you see it for the first time, it looks really convoluted and impossible to understand, but it's actually a great little chart. And if you get involved in any HVAC activities, you'll get pretty familiar with the psychometric chart. The vertical lines are degrees Fahrenheit, and then you add in the horizontal lines, and that's the moisture content of the air. So in pounds. And then you've got your delta T and temperature range, and then your curved lines on there are your relative humidity. Basically what you can do, and this is just the final slide on this, so if you know what your delta T range is going to be for a particular climate zone, and you know what the relative humidity is, you can determine where the dew point's going to be, so you can determine if that's going to happen inside your wall. It's a better way to measure problems with potential building assemblies, but it's still not an absolute, because it doesn't take into consideration the storage of the materials. It doesn't take into consideration, it's just a point-in-time measurement. And it's just telling you that not necessarily just a point in time, but it's just a point as to where the moisture vapor has the potential to become bulk moisture. So it still doesn't necessarily tell you that you're going to have a problem with your wall assembly.
You just stand in there with your wet and dry bulbs and spin them around?
With the sling psychrometer and get the wet bulb temperature and... Yeah. But again, all that's going to tell you is at that point in time, based on what the relative humidity is right then and there, and the delta T is right then and there, do you have the potential to reach the dew point inside your wall cavity? And you certainly don't want to have wall assemblies that have a high potential of that, but just having the potential of that doesn't necessarily mean you have a bad wall assembly. That goes back to what I was saying about the dryability. Most of the time, and why in this region we really don't have too many moisture problems, I guarantee you we get a lot of buildings that have condensation inside the wall in the winter. But we have enough period of the year that it can dry, and it has the ability to dry out. That material doesn't hold the moisture. As you get out towards the coast and we have significantly more humidity, significantly more rainfall, the same condition becomes fairly problematic because the material holds the moisture. And that's what, so again, we sort of just stepped up in levels of scientific ability and performance. I'm not going to go through all these. I want to get to the last part of it. I think you guys all get this. So if you have, with the psychometric chart, if you've got the relative humidity and you've got the temperature differentiation, you've got the delta T between inside to outside, you can determine what your dew point's going to be. So for this example, with 23 degrees on the outside, 70 degrees on the interior, we've got a delta T of 47 degrees. Calculating that out, we're going to get a dew point of 38 degrees Fahrenheit. And the temperature, I won't make you go through that calculation. So the temperature of our condensing surface, I'm sorry, we get a dew point of 37 degrees, but the temperature of our condensing surface is 38 degrees. We've got a wall assembly with little to no chance at these conditions to have moisture problems. And where this is coming from and where the dew point method is kind of starting to get pushed aside and not used as much is because it's not an absolute, but then coming in here with a situation where I don't have the slide in here. Shoot. Well, one of the biggest things is with putting and now required by code is putting this extra R5 insulation on the outside of the wall. And what happens is, and I can't show you, I don't have that little pencil thing. So the outside, our exterior temperature is 23 degrees. By adding extra insulation on the outside of the wall, we're raising our temperature inside that wall cavity. So in certain instances, it's creating a situation where we're improving the dew point, but in a lot of situations where I'm going to have to bring those slides back to better illustrate it, but as you increase the insulation in the wall, so for example on this one, as you increase the insulation on the wall, less of that heat is going to migrate out towards the condensing surface. So if you can see, for example, in here, we end up increasing the insulation here in this wall assembly. What makes this 33 degrees Fahrenheit is that we're getting conduction and convective heat to go into and towards the outside of that wall. If we add insulation in here, we increase the envelope on the inside, we're actually going to get less heat directed towards that exterior condensing surface. So all of a sudden, instead of this being 33 degrees, that temperature is going to drop significantly. Make sense? I'll bring a slide next time and show you that. I thought I threw it in there, but I didn't.
Is the 70 degrees there the temperature inside the
That's inside the house. Yeah. And so this is the angle of that is the temperature drop inside the wall cavity. So the whole point of it, forget about all these slides for now. The only point I want to make is that by trying to evaluate the wall assembly just using the dew point method, it's going to be incomplete, and it may or may not give you a true picture of your wall performance. The two main, and this is what I want to get to, and the two main programs that are out there that are available for profiling are NIST and WUFI, and the one that I've used primarily and the one that gets used more now is the WUFI. And what it does is taking into account the assembly data. So just in that slide that I showed you, you're inputting all of the information for your assembly, the amount of that material, the perm rating of it, and the program's got a lot of the data already in it. And you're actually putting in the climate data for your particular area. We talked about the climate zones previously, and each climate zone has its own data, but you can actually get weather data points for, there's 5 or 6 different ones just in Missoula, and so they're very specific weather point data. It's got heating degree days, cooling degree days. average rainfall, and so you take your wall assembly data and you take absolute specific regional climate data, and then what the WUFI does, and WUFI is a German acronym. It's Wurf und Feldheit something. I don't know what it even stands for, but it's an excellent program. But it creates your wall profile, and it measures the movement through and accumulation of moisture in your wall assembly, and that's the big part of it. I just mentioned about building failures. It's not necessarily just having moisture in your wall. I think a great number of wall assemblies have moisture in them, but it's the accumulation of moisture. If you have the potential for that bulk moisture to form, it's not necessarily going to degrade your building. It may, depending on the type of insulation you use, decrease your effective R value, but if that wall cavity has the ability to dry, it's not necessarily going to be a detrimental effect. So again, the WUFI measures the movement through an accumulation and then evaluates the potential for the interstitial condensation and the ability of that material to dry. And so it can measure it not only in how much potential and what the, and it'll run a model. It'll run an hour by hour, day by day, year by year model based on the climate data, and start to predict what the moisture content's going to be of your wall assembly. And it can tell you directly if that has the ability not only to have condensation, but based on your climate data and temperatures, will you have mold growth? So again, here's just the what did I say happens when your phone rings?
Go a solid dollar.
Here's just a sample profile of it, and here's again what it looks like, and you can kind of see this is an assembly for a brick wall airspace, OSB, poly sheeting, insulation, and so you can get a run of your temperature variations, and you can see your moisture potential, and basically this is really in that tiered level of what really is effective to test your building assembly. This is the only one of those that's really going to give you the true picture. So again, if we're talking about buildings here in western Montana, we're pretty spoiled because we don't really have to run a wall profile. We know that if we create a situation where we've got significant vapor drive and then a condensating plane towards the outside of our wall cavity, we're going to have moisture issues. But if we just add what I would say most buildings and most builders, an adequate or par air barrier to stop some of that or slow it down, we've got enough drying time. We have enough periods of time with very low relative humidity that we're not going to get excessive storage of moisture in our materials. So, does that make sense? Partially, sort of, maybe. But there's been a lot of, sort of in the last, there's a big wave in the last 5 or 6 years, builders really talking about the dew point inside the wall and really getting really, really excited about dew point in the wall, and probably doing a lot more than they really need to because they didn't have a complete wall profile. So the dew point method and some of the other rules of thumb can work when you're in their extreme, but if you're looking at something real effective, a full modeling of this is important. So that's the first part of it. We'll wrap it up there. When we're looking at system design, that thermal envelope is the biggest system, and it's the first one that really needs to be evaluated and at least create your baseline. So now as you're designing and you're evaluating your other systems, you have something to evaluate it against. And we'll talk about the other systems. We'll talk about various changes that we can make for efficiencies and how they're going to affect the envelope and how envelope changes are going to affect the other systems and so on and so forth. So. That's it. Any other questions, comments? You're now off the record. And let me know if you guys have any trouble with that quiz. I will say, and they're not in here so I can say it, but if the quiz closes at midnight, don't email me at 11:45 and say I can't get on the quiz.
Well, what if you were saving it for later to go in and recheck all of your answers and it was like 11?
I don't,
At 11 instead of 11:45.
remember that I could, every time you log on, Moodle picks it up, so if you say you were on 3 times before then and